Okay, I see your recording has started. So welcome back to the second day of our workshop on the Scalasca toolset. And just to remind the people who were here on the first day, which was not yesterday, but was Tuesday, we gave an introduction, and then we started using the tools ScoreP and Cube to do some measurements of an example application, and then look at those with the Cube GUI. For those of you who missed it, we'll quickly recap today, but I won't be, of course, going into the same detail. The recordings are available from yesterday. I see they're already on the Archer website, so people who missed them can, if they need to be, go back and see everything in detail. The slides are also, I think, either linked from there or available from there as well. The format for today is similar to what we did on Tuesday, that we'll have presentation and demonstration of the tools this morning using the hands-on example on ARCHER2 that we started working with on Tuesday. And then the afternoon session after the lunch break will be dedicated to working with you, helping you to work your way through the example if you weren't able to follow it this morning, or working with your own code. I know that a number of you were able to do some measurements using ScoreP of your own codes on Archer yesterday, or on Tuesday for that matter. So that's great. Maybe we'll have a chance to look at those together with you in the afternoon session. Those of you who are still catching up will also help you on the way as well. But the focus today will be the trace collection and trace analysis using the Scalasca toolset. That's what we'll start with, and then there'll be some additional presentations, one of which will help you to figure out what additional things you can do with ScoreP to not only filter things out of the measurement, but also to add things that you might be interested in having added to the measurements. So that will be a presentation that we'll follow on this morning. And then if we have time, we'll look at some case studies of applications we've looked at with Scalasca and ScoreP on not on ARCHER2 because it's very new, but on other systems. So that's the format which we have for today. If there are no particular questions and I don't see anything in the chat, then I think we can get started. So let me go to my Scalasca presentation. Okay, so trace analysis with the Scalasca trace tools. We didn't do tracing yesterday for the very good reason that if it's not done carefully, you can end up with some very large traces that are very difficult to work with. If you're really unlucky, you'll fill up the file system and the sysadmins will be quite unhappy. These are all sorts of things that we'd like to avoid, and that's why we've started up with this approach of doing an initial measurement, which is a profile measurement, scoring that measurement, which is a way to figure out what should be retained in it, and then hopefully that will guide us to what we really want to see and look for in the trace analysis. So an event trace is just a collection of events of what's happening on all the different processes and threads, which is time-stamped, and by doing an automatic trace analysis, we can distill that large amount of low-level event information into something that's higher level and hopefully still as insightful. This isn't the same as using a tool like Vampire or some other trace visualization tool where you can interactively zoom in and just focus on parts of the execution. But it gives you a high-level summary of everything that was collected in that event trace. That has a few advantages. It's of course automated. It's faster than having to do everything yourself, and it's also guaranteed not to miss anything because it can cover the entire event trace. It will also allow us to get a bit more detail than we were able to obtain from the profiles, because we see what's happening concurrently, or we can analyze what's happening concurrently on different processes. We can relate the events on the different processes, whether it's a collective operation or point-to-point operations. That allows us to identify wait states where there are waiting inefficiencies between different processes and threads, and those are the things that are the main focus of the analysis that we provide, where you can get quantification of where those inefficiencies are and whether they're worth trying to resolve in some way. We can also go further and look into try and identify the root causes of those inefficiencies as well, because in the trace we can go back through the history of events and figure out what was happening before the point where we ended up waiting. So the diagram on the right-hand side here is showing the three dimensions of performance properties, call paths, and locations. That's exactly the same format as we had in the profiles from SCORP yesterday. And so what we will see that we'll end up using the same GUI to look at that analysis. So Scalasca has been developed over, I think, more than 15 years now. It's developed specifically for scalable trace-based performance analysis. It is focused primarily on the most popular parallel programming paradigm. So that's MPI for message passing between compute nodes and between processes, as well as OpenMP, and to a more limited extent, POSIX multi-threading between threads within a process within a single compute node. We're working on extending that, but those are the paradigms that are currently supported by the Scalasca trace analysis. The trace analysis was initially developed on our BlueGene systems, where we had here in Jülich in Germany for a number of years. The largest measurements we did on those were up to 1.8 million threads running concurrently on that system. In that configuration, we're dealing with relatively large traces, and it becomes even more important to minimize and optimize what information is collected in the trace. But by using a parallel replay approach to the trace analysis, we can exploit the resources that were used for the application execution, where the trace was collected, also for its analysis. So for each application process which we collect a trace from, we would use the same process or the same core for the trace analysis of it. Basically replaying the events and comparing what's happening, the timestamps of the events on the different processes and threads. Of course, what works at very large scale can also be used at smaller scales as well, and that's something that could be done on a laptop system or a desktop system, as well as the ARCHER system, which is also quite sizable, or becoming quite sizable as well. So Scalasca works with SCORP. It's based on the SCORP measurement infrastructure, which we introduced and you had a chance to use on Tuesday. It's using common file formats for the traces, which are in a format called OTF2, Open Trace Format 2. And the analysis reports produced are in the cube format, which is also the format that SCORP was using for its profiles. Like SCORP, it's open source, available with a 3-clause BSD license, and has been successfully used not only on the BlueGene systems and a variety of Cray systems, but also other perhaps more exotic systems as well, such as the Fujitsu systems in Japan, Intel Xeon Phi, etc. There are a number of limitations to trace analysis, which are mentioned on the slide here. Hopefully they don't constrain things too much for many of you. The trace analysis is limited to the MPI thread funneled level of support. So if you're using serialized or MPI thread multiple, unfortunately the trace analysis isn't able to handle those traces. If you're lucky, you'll still be able to get the profiles from SCORP and analyze those, but not the trace analysis. The trace analysis also doesn't look at what's happening on accelerators. So if you have device events from CUDA or OpenMP, any nested parallelism, any additional events, those are also problems for the trace analysis as well. So the analysis is focused on the basic MPI and OpenMP interaction, and it will ignore hardware counter metrics, which are more suited for the profile collection, as well as those additional events from additional devices. So this workflow on this slide here shows recaps kind of what we went through yesterday. We're starting off with the application sources. We work with the compiler and linker to instrument those and build an intermediate executable. And then when ScoreP, working with the compiler linker, links everything together, you end up with the application executable linked with the additional ScoreP measurement libraries and any external third-party libraries like for accessing the hardware counters as well. When this application runs, that's the idea of the stacking here. During execution, it will be collecting in-memory profiles from each of the processes and threads, and then at the end of the execution, it will collate everything together and write it all out into a summary report, which are the cube files. And that cube file we can do some post-processing of, or we can look at it directly and then interactively examine it with the cube GUI. That's what we covered yesterday. High-level information about what's happening on each process and thread, which parts of the program those events were coming from, and then metrics that are derived from them, the execution time, the number of bytes sent and received, number of times routines are executed. That's fine as far as profiling goes, but we also saw that collecting everything can have a side effect of too much dilation, too much measurement overhead. Measurement overhead is usually more of an issue for the trace collection, but it's also an issue for profiling as well, because every time we time an event, every time we have to aggregate the time for that event into the profiles that are being collected in memory, that's some additional cost. So we can use an initial measurement and refine that to optimize the measurement configuration. So that's the scoring, which we did yesterday, that allowed us to identify some frequently executed routines which were causing a lot of measurement overhead and not really adding value to the profile because they were distorting the timings of the events substantially. By using the scoring, we can focus on the small computational routines that are not so critical for our inter-process, inter-thread analysis, but still retain all of the MPI events, still retain the OpenMP events, and therefore still have a good analysis of the inter-thread synchronizations and inter-process communication and synchronization. We'll see later how we can also augment those measurements if we wanted to add hardware counters or other information to them. But basically, we did the basics yesterday of taking a measurement, getting a profile, and refining that, and then examining those in the cube GUI. You'll have seen in the ScoreP scoring various references to trace buffer sizes and aggregate trace sizes, and that's was what we were warning you about, that if you were just to plow ahead and turn on trace collection, you might be surprised by how large the traces get very, very quickly. And very large traces become a problem, not only in terms of storing them in memory during measurement collection, writing them to disk, but also for any sort of subsequent analysis as well, because large traces at some point also need to be loaded into memory, and having lots of memory for that is also a challenge as well. But by deciding what is appropriate to keep in the trace, that means that when we do the trace collection in memory, when it comes to the point of storing those traces, writing those traces, we write a trace for each process, for each thread, ideally at the end of execution where it doesn't disturb the process execution that we're measuring. If it doesn't make it all the way to the end of the execution and the buffer is full, it will have to pause execution, write that trace, clear its buffer, and then it can continue. But while one process has been paused to do that, the others are typically waiting. They're needing to interact with that process to communicate with it, to exchange messages with it. And so the writing time for the traces of one process end up as waiting times on all of the processes that interact with it. And as a cascade effect, all of the processes that interact with those. So that cascade of waiting tends to work its way through all of the processes. They all end up waiting while one is writing. Once that one has finished its writing and continue, they can all proceed at that point. But if you're unlucky, then one of the other ones will have filled up its trace buffer at that point, and then it will go through this same process. So you end up with a sequence of these cascading stalls where we're flushing events to disk. We really want to avoid that. We don't want the large traces in the first place, and we certainly don't want to interrupt the measurement which we're doing to be able to do those intermediate flushes to disk. So ideally, we want to make sure that the trace buffer that we provide for each process is adequate for storing all of the events that will be collected, and then only write those events at the very end of the execution. I mentioned that the trace analysis is based on a replay where we restart processes. We start the analysis processes on the same compute resources. Those load in the event traces, work their way through those trace events on each process. They replay the communication. So whenever there's a communication event that is in the trace, that's what we would replay in the analysis. Comparing what's happening on the different processes and threads at that point allows us to calculate the waiting times and other information that we can store. And then at the end of that analysis, we would write an augmented profile, an augmented wait state report. So not only the basic timing events for MPI and OpenMP operations, but also breaking out what proportion of those times were waiting times in a variety of different categories. So that analysis report is then in the same format, same cube file format as the initial profile, and can be examined and explored with the Cube GUI in the same way. So this augmented report will have additional metrics. It will therefore be larger than the summary report. Typically, we are collecting, it depends on the programming paradigm. If it's MPI, we have certain metrics that are derived for that. If it's OpenMP, there's different metrics for those. So the size of the profiles will be proportional to the processes and threads that are being collected, but it's typically a small factor compared with the profile summary. The event traces are a completely different scale. Those will often be terabytes, petabytes in size if you're dealing with many processes and threads, and it just depends on how long you are doing the measurement and how frequently those events are being recorded. Once we have completed the analysis report, you may not need the trace to be retained any longer, unless you want to redo the analysis, which sometimes is useful. The other option is that you may have some other way of visualizing the trace. You can use Vampire or potentially other tools to examine those event traces and perhaps get some more insight as to where to look at them. But typically the traces are not necessarily what you'd want to keep for a longer time. Once you've done the analysis of them, then keeping the analysis report doesn't have all of the information, but it certainly has the most important information to be retained. I mentioned a number of metrics that the trace analysis can determine that are not available when profiling. When we're profiling, we don't want to interrupt the measurement to exchange timing information or additional interactions between the processes and threads. So we can't compare timestamps at that point. but when we're doing the trace analysis, we can take our time for that. And that means that we can go through the traces that have been collected for each process and carefully compare the event timestamps. So if we look at a very simple example here of just two events from two processes where we have a send on one process, a receive on the other, these are blocking events. That means that if the receive is occurring before the send is initiated, the receiving process will inevitably have to wait until the message has been sent, has been at least ready to send, and then at some point the send will proceed and the receive will complete. If the send is before the receive, it may already be able to complete before the receive, but in this case it's the receive that has been executed early, and what we're showing here, what's marked with the yellow arrow here, we can assume it is waiting time. The receive is blocking, it has nothing else that it's really able to do until the corresponding send is initiated. There may be some rendezvous going on inside MPI, so we don't know exactly when the send event is actually initiated. We don't really know when the receive is completed, but when we're told that the MPI receive is completed, we know that the date has been transferred. And we know that it can't have started until the corresponding send was initiated here. So this is the information we get at the MPI library level. There may be all sorts of other things going on within MPI, but the latest point where the receive could have started is the earliest point where the receive could have started is the part that's corresponding to the initiation of the MPI send. So we call this late sender time, and we would associate it with the receiver process here. The same thing happens also for non-blocking events. There, it's not the, if we look at the case on the upper right-hand side here, we've replaced our blocking receive with a non-blocking receive. We can then do all sorts of other stuff and then come back and complete the operation with an MPI wait. The MPI wait is necessary to complete the receive and verify that it's finished, and until it's finished, the assumption is that the receive is still in progress. If the MPI wait is initiated, in this case, before the corresponding send, that means it will be the MPI wait that has the waiting time. So the wait has now been transferred from the blocking receive on the left, the first example, to the blocking wait operation, which has to wait until the corresponding send has been initiated. The same happens in the other cases as well, where it's maybe a non-blocking send, but until the corresponding send is initiated, there needs to be waiting time on the receiving process. So those are simple examples. We'll see a few more in the course of the exercises and the rest of the day. Another thing that we can get from the trace analysis is an idea of what is the critical path of execution. Again, here we're showing a representation of the execution timeline of three processes. They're executing a variety of functions. They're sending data between themselves. And when the receiving process is before the corresponding send, then that part will be quantified as waiting time as part of the receive operation. So we have some waiting time on the first rank while it's waiting from the message from the bottom one here, and then we have some waiting time on the middle rank while it's waiting for the send to be initiated from the first rank at the top here. We're also showing waiting time at the end, where we're assuming there's some sort of barrier or some sort of collective operation before the trace continues. For the critical path, we want to identify those functions that are responsible for progress, that limit the execution progress of the application. And those are now highlighted here with the kind of reddish outline here. That's starts with the process at the bottom. It migrates to the process at the top, where it's a different function that's being executed, and then to the process in the middle. The way in which the critical path is determined is working back from the end of the execution, seeing what computation is in progress at that point. So we ignore the ranks which are waiting. And then we figure out what was the event that was limiting the ability to start this event on the last process. And that's the message exchange from the first one. So that means that the critical path then moves to the top process here. We follow back what it was doing and what was the limiting event that prevented it from being able to start. Well, it was the message that was being sent from the rank at the bottom here. So that helps us identify the critical path, and it's worked back from the last event to the last event of whatever process or thread has been analyzed to one at the beginning. Those events that are on the critical path are the ones which are the best candidates for optimization, for removing parallelization bottlenecks, because those are the ones where if you can reduce the time, if you can make this execution of foo by the last process here shorter, then this send could be initiated earlier. That means there'd be less waiting time on the first rank. That allows the bar routine to start earlier on the first rank, and then progress can continue earlier for the middle rank as well. If you also reduce the time of bar on the top rank here, then that means that again the send and its corresponding receive can be completed earlier, and progress can complete much faster. If, on the other hand, you reduce the time in some of these other events, for example, if we reduce the time in bar in the middle here, that won't result in any reduction of the overall execution time. What it means is that the bar event here becomes shorter. The mouse isn't showing very well, but if we shorten the time here, we just start this receive earlier, and we have more waiting time in that receive before we can continue with the final event here, the foo bar event. So only by reducing the time of the events on the critical path can we hope to improve the total time of execution. Another analysis possible from the detailed trace analysis is not only figuring out what proportion of the time in the receive operations is waiting time, but what are the causes of those waits. So if we do our wait state analysis, we can figure out that there's waiting time here for marked in kind of yellowish color for the receive here before the send is initiated. There's also waiting time here on the bottom process, but part of the waiting time on the bottom process was actually was waiting on the send coming from the middle process, but that was a knock-on effect of having to wait for the top one here. So we can break down what proportion of the waiting time is a direct consequence of a message transfer. That's the parts that are marked here as the direct time, as well as the parts which are indirect. They're not coming from an immediate event, coming from a communicating process, but they're a knock-on event that has already been quantified on some other process. So the direct waiting time here of the middle process can be attributed as indirect waiting time for the process at the bottom here, as well as its direct waiting time. So this helps us get a little bit more insight into what is the origin of the waiting times. Is it exclusively a communication sequence, or is it a result of some additional computation, some excess computation? This middle case is waiting time. but the waiting time of the middle process is a result of a delay in completing the computation of the top process here. So we can then break out that as delay costs, and those delay costs are, again, indicators of potentially load balance or excess work that are the things that you'd want to minimize to be able to get a faster execution and more optimal execution with less waiting time. Okay, that's the broad theory of things. How do things work in practice? This is where I would go back to the example that we worked with on Tuesday. I think that most of you said you were able to follow that example. I think there's one or two people I see that may have missed that, so I'll just quickly go through what we covered on Tuesday, and then we'll see how we can use Scalasca not only for tracing but also for profile summary analysis as part of that. We're going to be using the Scalasca command. That's one command that can do everything that we need to do with Scalasca, but there's also shortcuts which you can use if Scalasca analyze, Scalasca examine are a little bit long-winded. Those can be shortened in various ways. So we'll be looking at a command called scan for doing the measurement collection and analysis. There's lots of options which I don't want to discuss in any detail at the moment, but we'll be using the scan command or the Scalasca analyze command as a preposition to your launch command. So where previously you were using srun or MPI exec, we would preposition that with scan with some configuration options, and then it will have the ability to control the measurement that we're doing. You don't need to do that. You can just run the instrumented executable as we did yesterday with on its own, but we'll see some advantages, some convenience that the scan command provides in a moment. The scan command does a few things for you. It will do some consistency checks. It will do some automatic setting of environment variables, so setting up the measurement in ways. Primarily, that's switching between the profiling and tracing mode, but in principle, it also will be setting a reasonable default experiment title if you don't explicitly set something on your own. So, as we saw yesterday, you can set, you can configure things with Score P by setting environment variables. That gives you complete control of things. These are just a few extra defaults that are a convenience option. So it'll be checking the executable to check that it's instrumented. It will check the execution configuration of your MPI exec or your srun command to work out how many processes and threads it believes it's being asked to execute, and then it will just use that information to set an experiment name or experiment title, which can help distinguish different measurements that you might be doing. The main thing that the scan command offers is that it allows you to combine a trace measurement collection with the automated trace analysis, because as I said, the trace analysis we would want to do with the same number of processes and threads as the measurement, and that's what you have already specified in your job script. That's what's already available from your MPI exec or your srun command, and so that's why providing that information to scan, the Scalasca analyze allows us to extract that information and then reuse it for the trace analysis replay as well, and that's the main convenience that you'll get from this nexus, from this scan command. We also briefly introduced a square command yesterday, which is a post-processing option. So instead of just looking at the basic profiles and trace, sorry, the basic profile that is provided by Score P, we could do some post-processing of that, and we'll see that in a moment as well. So you had access to Archer yesterday. we'll just go through the process of making sure you're set up to continue that today, making sure that we have the Scalasca module loaded, and then work through the example, which was the BTMZ example that we worked with yesterday. Okay, so let me drop out of the slides here. I'm going to log into Archer. You'll notice that I'm using the -y option because that's the option that enables the X forwarding that I'm going to use when I use the GUI. You can use -x as an alternative. I'm now logged into my account. I'm going to switch at this point to the module that we need. So module restore program GNU. We have only the Scorpy and Scalasca installed for program GNU at the moment, and then module load Scalasca. So that was successful. Scalasca is on my path. Scorpy is on my path. So if I run the Scalasca command, it just gives me some basic usage information. I can use Scalasca examine if I want to get the options for the square command, or the Scalasca analyse, which is what we'll be using first, to get an overview of how we do a measurement under the control of Scalasca. So we have to work in the work file system. So in this case, that's work TA031, TA031, and then whatever your username is. I have some stuff from before, but I'm just going to start again just to recap things. We provided a benchmark example that's also in work, but in work Y23 shared tutorial in PB. So I'm just going to unpack that into my work directory and cd into that directory. Yesterday, all of you should have already done this. You should already be at this point, and actually well beyond this point, but just to recap. If I do make at this point, I get the basic instructions for building the example, which would be the command here. And that's going through the source files, building them, their Fortran sources, they're having OpenMP enabled, and at the very end, it links everything together and puts things into the bin directory. I cd into that bin directory. I'm going to copy the job script that we had yesterday. There are job scripts for different platforms, including ARCHER2. So we'll copy the run job script here. And since I messed it up yesterday, I need to make sure that we have the partition set here. And we'll just check. We have a different reservation today. So I'm going to uncomment that, and hopefully that will allow us to run in the job, the reservation. And then at the very end, it's just going to do srun with the executable here. So I'm set to run this in this directory, and hopefully that will run relatively quickly. It'll take about 10 seconds, 12 seconds. So that's our reference case here. So far, no Scalasca. So far, no scan. In the make file here, we scroll down the makefile def here, we see where the compiler is defined, so the Fortran compiler for the Cray system, and it's showing us a couple of alternatives here which we could use. This was the version that we were using yesterday. Another alternative is to have a preposition in the job script here. That job script that preposition allows us to add whatever we want, Scorpy user as a preposition, without having to modify the makefile, which is what I'll show you here, but you can choose whatever way of modifying your makefiles as you find appropriate. So first we'll do a make clean, because I don't want the instrumented objects that didn't have the instrumentation. And then I'm going to run make suite, which is just a shortcut for class and all the other things. And then MPI 77 will redefine it. By default, it is Fortran, but we're going to preposition score P, the score P instrumenter. And I'm adding a flag here for user instrumentation, and we'll see the impact from that in a moment. That's just enabling additional instrumentation that I already have in this benchmark. It's not something that will be in your code until you add it, but we're just showing you how to use that here. So all of the compile and link commands we see are now replaced by score P user, and then the Fortran compiler, and then everything else is the same. This benchmark is set up to work to put the instrumented version into a separate directory. So I now have the bin directory, which was my reference on instrumented version, and I have a bin score P directory, which has my instrumented version. The instrumented version is a little bit larger. It's actually linking in a lot of runtime libraries, so we'll see the instrumented version is quite a bit different from the uninstrumented version. So let me go into this directory. So now I have an instrumented version which I could run. I'm going to then copy the job script. For first test, I'm just going to use the job script that I already have. So here we're getting a default measurement from score P. It's creating a temporary directory where it's going to store the measurement, and at the very end it will rename that. In that directory it has a couple of files, but it's not complete at this point. Until the profile is there, the measurement is still in progress. So let's see how we're getting on. Takes a few moments, still running. So it's this instrumented version we already noticed yesterday is quite a bit slower than the uninstrumented version. Now the measurement is complete. The temporary measurement directory has been renamed, and it's been given the only name that score P could come up with, which is the timestamp and the date timestamp. Sorry, the date and the time, and some unique identifying information. But this directory now contains the profile.cubex, which we looked at yesterday. I don't propose to look at it right now. But basically, the key thing was that we could score that profile. Alternative way of scoring it is by using the Scalasca examine or the square command with the name of the directory. So this will be post-processing the profile.cubex into a summary.cubex, and also putting the score report into that directory as well. Now I have the score P score file, as well as the summary file, which has the additional metrics generated by post-processing. If I look at the score file, this is where we were seeing the information about estimated trace sizes. So by default here, we're going to get something like 160 gigabytes of trace data, for which we had 8 processes, so that's roughly 20 gigabytes per process. I don't recall how much memory there is available on an Archer compute node, but 160 gigabytes is already quite a lot. It's also quite a lot of data to be writing to the file system as well, especially since we were running for something like 10 seconds. So we've got something like 2 gigabytes of event data per process per second. And you can imagine if we were running this for a reasonable time of a few minutes or maybe an hour, you'd quickly end up with terabytes of data that would be completely impractical to store in memory, and not able to write into, or you need the space on the file system to store that as well. What we're seeing here, additional hints as to where that 20 gigabytes is coming from, and it's mostly from what are called user routines. So the user compute, sorry, too many clicks. Here we're seeing there's somewhat 6.5 billion visits, 6.5 billion events, that we need roughly the full 20 gigabytes on each process for what are user source routines, things that were instrumented by the compiler as routines in the application sources itself. A relatively small amount, 32,000 events, roughly 300 kilobytes, is for MPI events, or for the OpenMP events that we instrumented as well. The OpenMP is a little bit more in this case, but it's more manageable, more reasonable than having all of these 6 billion events. So what are the 6 billion events? Where are those coming from? This is the region-wise breakdown that we're looking at here. We see in this sorted list, there are 3 routines that have been executed more than 2 billion times by each process, and which consequently require about 7 gigabytes of trace buffer to store those events. Those are likely to be the main cause of the dilation which we had, the slowdown in the measurement, and they correspond to the majority of the space that would be needed for storing the traces, the trace buffers. There's also a few other routines here which are a little bit less critical, but those are also executed frequently enough that it'd be worthwhile eliminating those as well, just to make the traces smaller and more manageable. Then in this list we come to the OpenMP parallel regions, which are what we're interested in. Those are much less frequent. We have inside those, we have the barrier synchronization and everything that goes along with that. And then further down this list we'll find some more routines. These routines are matched as marked as COM routines rather than user routines, because those are routines which contain either MPI or they contain OpenMP in them. So those are common routines which are routines that provide us the context to understand where MPI and OpenMP is used. So those are routines which are more valuable to retain. We don't need to retain them. You could be filtering them out as well, but there's relatively little benefit, and actually they're not causing a problem. So those are valuable routines to have, and there's more of them that we'll see down here as well. And then further down this list, we're getting into things that are called much less frequently, but there are also things that are not necessarily useful to retain. Timer clear, timer read, timer stop. So these are internal routines for the benchmark. They're only called a few times, but in principle, we're not interested in those, so we could filter those out as well. I don't want to spend much more time elaborating on this because I want to see how things change when we use Scalasca. So if I use the job script that's provided on ARCHER2 for Scalasca, let's copy that to the directory. I'm going to edit it because I need to change the partition if nothing else. So uncomment the part to enable the partition and the reservation. I'm going to load the Scalasca module so that I have access to the scan command, so that when I prefix the scan command on the srun, now I have the measurement execution under the scan control.
Brian, there is a question in the chat. I think some parts might have been a little bit too fast. So could you please put the history into the chat?
I'm not sure that's really going to help, and it's actually not critical for people who have gone through things yesterday. This was, I think, the main command that you would need to be able to build the executable if you didn't build it yesterday. If you already have it instrumented from yesterday, there's no need to repeat that. And running the uninstrumented version is also just for reference, so there's nothing critical there. The main thing is that we are now going to be using Scalasca, so that's why I'm using the Scalasca job script here, and it's quite complete with that. As yesterday, the partition needs to be defined. I'm using the reservation, which is set for today. If you don't set the reservation, it should still run, but in the normal queue. What I changed, or what's different from the default execution, is that I'm loading the Scalasca module because I'm using the scan command, and if the module isn't loaded, then the scan command won't be found. Yesterday we strange editor here. We explicitly defined a score P experiment directory. I'm purposely not doing that. I'm just going to leave it undefined. So you can define whatever you want here as the measurement directory. If I can spell it correctly. ECTORY. So define whatever you want there, but if you don't define something, we'll get something that scan produces. If I run it without specifying a filter file, which is what we already did, then we wouldn't be doing the filtering. Yesterday we defined a filter file. I'm just going to use that here with the scan command, and so we'll see the effect of that filter file. Just submit that to get it going, and then take a quick look at the filter file which we saw yesterday. It's just listing a name of the names of a few routines that we identified as potentially useful to filter. I wanted to test that filter file with my initial score P measurement, then I can do so. And that filter file would be validated, telling me which routines it matched, which routines it retained, and what is the impact of that. So here we're seeing by the pluses that we have 6 routines at the beginning that are matching the filter, and that filter is then removing the 21 gigabytes of information from each process that we didn't find worth retaining. Also telling us that the size of our new trace, if we were to do a trace measurement at this point, would be now closer to 100 megabytes per process, 700 megabytes in total. This is quite a bit less than the 20 gigabytes or 160 gigabytes for the total execution. Okay. So that's our filter file that we looked at yesterday and verified. What do I have now in my directory? Well, I see the new measurement directory here, and if I look at the job output, it'll perhaps show me a little bit more about what's going on. So it's giving me some commentary here at the beginning, telling me what it's doing. So it's going to be using a measurement directory that it has chosen based on the name of the executable. So we gave it, this is the name of the executable. From that, it derived a base name for the experiment, and it's also telling me what configuration I'm using as well. So 8x6 is 8 MPI processes, each with 6 OpenMP threads, and then it's a summary measurement because we'll be distinguishing that from the trace measurement that comes later. And then we launch the srun command. So the scan command has taken the srun command, processed it, processed some other environmental information, and then gave us the command that it's going to run, that it ran to actually get the measurement. At the end of measurement, it tells me that it's complete, and And we see here that with the filter file applied, we're back down to roughly the same 12 seconds that we had for the uninstrumented execution. So all of this is essentially the same as what we did yesterday with score P on its own, but just using scan to provide us a little bit more comfort, a little bit more convenience, and to set us up for what we're going to be doing in a moment. I think at this point I can switch back to a few slides which basically kind of summarize that. So using, the slides don't go through all of the instrumentation which we had covered on the slides on Tuesday, but how we copied the Scalasca batch script and how we prefixed the srun command either with srun or with Scalasca analyse, so that when it runs, we see that the job output tells us what it's doing. It's this shouldn't be here. It should just be the name of the executable here, not 8x6. But it chose an experiment directory, which is a little bit more meaningful than the date and the timestamp. I don't think I did the post-processing, but I showed the post-processing with the initial score P file. Showing it with the new measurement would be more or less exactly the same. All of that was a very quick run through intended as a recap of what we had seen before, where by doing the post-processing, we get some additional metrics. We break out the time from the time goes into MPI time, OpenMP time, and then into subparts. So actually, let me quickly go back and look at that. But, we covered that also very quickly yesterday. This was the new measurement. Because we specified a filter file that was captured by score P, we have our profile that was generated. What the scan command also did was it stored a copy of the execution output in this log file in the subdirectory. So it's just for reference, as well as the filter file, which you would need for redoing this measurement, as well as the config file that shows how the measurement was configured, all the environment variables. We've also stored the log file. So those are the information that summarizes what we have in that measurement directory. If I do post-processing of it, the square command or Scalasca examine, it's taking that profile and generating the additional metrics for the OpenMP and MPI execution times from it. And bringing up the Cube GUI. So whereas in the profile we would just see the total time here, in the post-processed version, I can then expand that into the various parts, which are the purely computational part, the time that's in MPI, the time that's in OpenMP. If I select the MPI part, I just see the time, the MPI time, in this case, the 3.7 seconds, where that has been spent. And by expanding the call tree appropriately, I can see that most of it is in the wait all. I don't, at this point, I can go further here. I can see how much of it is synchronization time in the MPI barrier. I can expand the communication and see that the wait all is, or the waiting time here is, not the waiting time, the time for the send and receive, which is point-to-point time. The wait all time is being shown here as request handling. So it's, here's the request completion, which is the wait all time. So this is just a different way of breaking out the MPI time into constituent parts, and then being able to identify those and see where they are, what time is on each process. And in this case, the MPI is being executed outside of the parallel region, so it's only on the master threads on each of the 8 processes. If I look at the OpenMP time, it's mostly in this ADI part, and then we see X, Y, and Z solvers doing parallel execution, and then we can see not the time for the parallel computation. That would be in the computation metric here, but we're seeing the OpenMP overhead here, which is actually synchronization time, barrier synchronization time, and that's the implicit barrier at the end of the different parallel regions. So for each of these parallel regions, and there's a lot more, inside this parallel region, there's a number of do loops, an implicit barrier at the end. Some of the do loops have their own barriers, some of them don't. So there's a lot of implicit barriers. There's no explicit barriers, OpenMP barriers in this execution, but those would be distinguished as well. I mentioned that when we instrumented this application, we marked, we enabled some user instrumentation. In this case, we're actually marking 2 things. We're marking the main computational part, which is marked here as iteration, and we disabled measurement for part of the initialization. So there is, of course, execution time for that initialization, but by saying we don't want to record it in the measurement, then we just don't see it. We see the time for it, but we don't see any of the details for it. I believe that I can look at the source code, and then it will show us what that instrumentation looks like. So we have a header file that we need to enable the macros, and then this was where we disabled measurement using the macro for recording off. After we'd finished the initialization, we turn the measurement back on, turn recording back on. And then further down here, we have the region that we marked as iteration. So this region here, let me do it this way. Here we have a region which is marked as iteration, and it's defined at beginning here at the start, finishing here at the end. And everything that's inside that then becomes, or having defined that region, anything that's called inside it then becomes a child of that region. That allows us to distinguish the routines in here. So here we have Exchange, QBC. Here we have ADI. We're seeing them marked here. And they're distinguished from ADI and Exchange QBC, which are executed. I don't have a way of returning other than to go back here, I guess. So as part of the warm-up, before it was timed for this benchmark, those routines were actually executed outside of the measured region as well. So by adding this additional annotation to the source code, I could do 2 things. I could distinguish the initialization from the computational routine. I could have marked other phases of interest if I wanted to, but that was just a basic example that I'm showing here. And I was also able to disable measurement entirely, disable recording for part of the execution, which in this case was not so interesting. So that's where measurement was disabled. It was only because I wanted to enable that I needed the scorep --user to enable that instrumentation, to enable those annotations. If I just ran scorep on its own, those enables would be not active, and I would see the impact of recording everything and without this region being distinguished. You're welcome to try that this afternoon. It's something it's probably more interesting to use with your own code. I think I'm finished here. So where had we got to in the slides? Okay. There's probably not so much detail on the slides here, but we've gone through the basic steps of doing a measurement with an instrumented executable, scoring that measurement, applying a filter, and then the new measurement, applying that filter, is one that's a lot more reasonable for working with, for comparing the execution times of, and also for preparing for the trace collection and trace analysis, which is what I would like to move on to. I don't have to change anything in the instrumentation itself because we already have the instrumentation set up in a reasonable way. We already have a filter set up that we can use for the measurement as well. So the only thing that I would need to change to do a trace collection is to enable it. And before enabling it, I would want to verify that I have enough trace buffer memory reserved for those trace events. So here on the slides, it's showing a magic value of 100 megabytes per process. Where is that magic number coming from? That's coming from the ScoreP report. Here in the ScoreP report, it's telling me how much space I need on disk for a trace. So I have to make sure that there's roughly 700 megabytes available. That shouldn't be a problem, especially in the work file system. But it's also telling me how much I would need for each process. We initially, without the filter file, we're going to need 20 gigabytes. That's completely unreasonable. Here, 100 megabytes is a lot more reasonable. But 100 megabytes is still larger than the default. It's the default value. ScoreP total memory, the default value as reported by ScoreP info here is 16 megabytes. So because we would need more than 16 megabytes, that means that a trace execution would have a number of flushes in it. In principle, you can go ahead and do that and try that, but I'm just going to avoid that for now. I'm going to make sure that in the batch script here, bottom of it here, I'm going to uncomment the part that is saying 100 megabytes. The default is 16 megabytes. If I need 100 megabytes, then it would mean that I would have 6 or 7 flushes in the course of execution. They'd be done by different processes at different times, and therefore you'd have a lot of perturbation potentially in the measurement as a result of that. If I was to use the environment variables provided by ScoreP, I would do something like enable tracing here. True. Alternative way is to change the -s option of the Scalasca analyze to a -t option. I find that easier to remember than ScoreP enable tracing, but that's your choice. One way or the other, setting tracing to be true would allow us to do a trace measurement, and when the trace is being collected, that also triggers scan to do the trace analysis as a subsequent step. So leaving the score-p environment directory unset because the trace will be put into a different directory by scan automatically. Those are the changes to the job script. I'm going to submit here. And I hope that it's already started running. Looks like it. You already see that it has prepared the directory that it's going to be using. Give it a trace extension just to distinguish it from a summary measurement. And inside that, it has various additional directories, additional files that it's going to be using to store the actual trace data. And this file here, this OTF2 file, is the anchor file for analyzing the trace data. So how is the execution going? In the output, I see that it tells me which directory it's going to be using, and further down, when measurement is complete, here is the completion of the measurement part. It has immediately proceeded to do the trace analysis. And the trace analysis is done by part of the Scalasca toolset, one of the tools called Scout. Scout comes in different varieties for plain MPI or for hybrid in this case. There's also a version for pure OpenMP. So it chooses the appropriate analyzer, and it gives the analyzer the name of the trace that has just been collected. What the trace analyzer does is it opens that trace, loads the event trace data into memory. That's what it's reporting here. And then it goes through the events, replaying them as part of its analysis, and then writes the output at the very end. And it's also reporting at the end that there was 400 megabytes of trace data on disk. The reason that 400 megabytes is different from the 600 of the estimate is that there's where possible, score-p will try and do some compression of the data. It can't guarantee that. It depends on the timestamps. It depends on what events there are in the trace. But it's also a good idea to have a little bit more space available than actually necessary, so that here the fact that you got something like a 50% compression is in your advantage. It means that it was a little bit faster writing that data and also reading it back for the analysis. As we discussed here, if we no longer need that data, we could immediately remove it, but for now I'm going to leave it. And let's see what else is now in that measurement directory. Didn't disable profiling, so it's still there, but we have now an additional file that has been produced coming from the Scout trace analysis, and we also have a log file that's been produced by the trace analysis as well. That log file is the analogous to the score-p log file. Just having a record of what Scout was doing when it was replaying and doing the trace analysis. If there was an error or a warning, it should actually highlight that, but in this case, everything went successfully, so there's no need to be concerned. And the trace analysis file here is a little bit more than twice the size of the profile analysis. If we look at it with Cube, it's in Cube format, then we will see that there's a whole bunch of additional metrics that have been put into that file. So time and visits are what we had before, and then we have a number of additional metrics that have come from the trace analysis. Some of them have negligible or low values, but we have the late sender time, and we can figure out where that late sender time was occurring for the wait all here, as well as a bunch of other metrics that we could go through and look at here individually. There's a longer list of them. It's much better if we do the post-processing just to put some structure into this analysis. Instead of using cube here, I'm going to use square, and square with the directory rather than square with a file, so that it does the appropriate post-processing. It found a profile, so it post-processed that as well as the scout.cubex, and that scout.cubex is being post-processed into a trace.cubex file, and then it's that trace file that is a trace.cubex file that is now being displayed by the square command. So now we have a little bit more structure. We still have quite a lot of metrics here, but we have the time being broken out into its components, which we had before. All of this is what we had before from the summary measurement. But we also have, I hope you can see that there's some markers here that are there to guide you and suggest that there's some additional information, and those are the additional metrics that have come from the trace analysis. So the basic profile here with MPI time, with MPI synchronization time, MPI collective synchronization time has been augmented with the additional time, which is the wait at the barrier. Not the time in the barrier, but the time waiting at the beginning of it, and also the time that may be there for completing the barrier at the end. And here we see the barrier that is highlighted as well. If I right-click on the metric here that's highlighted, I hopefully can get some little bit more documentation for it. So this is on-down documentation of the metrics that should be available. I don't think it's working for the summary measurements on Archer, but that's probably something that Pavel can look into. But here for the trace analysis, it is, let me make it a little bit larger. For a barrier operation, no process can get past the barrier until all of them have reached it. So those which reach the barrier earlier have to wait, and will wait until the last one reaches it. So here with our three processes, we have two processes that are having to wait until the last one reaches the barrier. At that point, they can all continue, but the time that's marked in here is the time for waiting in front of the barrier. The same would be true for other collective operations where we have reductions. Here in the verify, we would have the same sort of behavior. It's a little bit different because it depends on what is the root of the barrier, sorry, the root of the reduction operation. Here we have it's the root that needs to wait for the other processes to complete the reduction. Where we have a reduce only on rank 0 here, it's not having to wait. It can already send its data to rank 1, and rank 1 won't have to wait for it. But rank 1 here will have to wait for rank 2 here to send its data, and so all of the waiting time for the reduction here is being shown just for one of the ranks. I'm not sure if we'll see that here. Yeah, so here root 0, rank 0 is the root of the reduction, so it's having to wait for the other ranks. We're seeing the time here is negligible, but it's not on all of the ranks. It's only waiting time on one of the ranks, rank 0. It's also not in our main computational part, so it's not something we'd be particularly concerned about. It's only in the verification stage, but we were able to quickly identify which parts of the execution were affected, which processes and which threads had that reduction operation. There's a little bit more time for the point-to-point operations, and it's showing us here that something like 40% of it is late sender time. There's a very small amount in the exchange and the initialization. There's a little bit more in the exchange here for the collective operation. Sorry, not a collective operation. It's a wait all operation, so it's actually waiting for multiple ranks, and the amount of time it will have to wait depends on which rank is doing the wait all, because it has. We see relatively lower values on rank 2. We're seeing much higher values on some of the other ranks. This is likely to be indicative of the fact that there is more work on rank 2, and so it is spending more time in computation, and therefore less. It's because it takes longer in the computation. There's less waiting time for the wait all operation in this case for that rank. Let's quickly check that. I look at computation time for the iteration. Rank 2 has a slightly higher value than the other ranks here, but it depends on which neighbors it's waiting to communicate with. It's not necessarily waiting on all of the ranks in this case. Keeping an overview of what's happening in all of the processes and threads can be a little bit challenging. So when they're all expanded here, you can't see what they're all doing at the same time other than doing some scrolling here. We provide a couple of other presentations. We can present things in a statistical representation. So this is just a box plot showing the minimum and maximum values, and then the intermediate values, which are the mean and the median. A violin presentation is a different representation of the same statistics if you want to see more about the actual distribution of values. For the sunburst presentation, we're seeing things for all of the threads at the same time. Sometimes this is helpful if we have a lot of processes and threads, but also this won't scale more than a few hundred. And here, when we're looking at the values, they're all being shown as a fraction of the total time, and all of these values are relatively small values. So that's why we provide some different presentation modes. The one that makes most sense here for processes and threads is the peer percentage. Now we're seeing the values as a proportion of the largest value. So rank 2 has the largest value. It's then being set to 100%, and all of the other values are then shown as a percentage of that highest value. The color coding here, going from red, orange, yellow through blue. If it's all red, they're all at the high values. Those which have slightly lesser values, some of them going down to 75, 77%. Those are more in the orange range here. But again, to get an overview of those, we have the colorings of them here. It's a little bit hard to figure out what's happening for each of them, but we also have a presentation on the right-hand side here, which is a more topological view. Here we're looking at processes on the x-axis. We have 8 processes. We have the threads per process on the y-axis, and so for each process and thread, we have a tile here that is color-coded. And from this, it's easier to see at a glance that we have a couple of threads. If I right-click here, it allows me to figure out which thread I'm looking at. So thread 0, thread 1, thread 2 on the y-axis. The red ones here are higher values, and that already indicates that we have a load balance between the first 2 threads and the subsequent 4 threads on each rank. If I look at something that is just one of the solves. So here the X solve has the same imbalance, the Y solve. For the Z solve, the imbalance is not quite the same, but there's also a little bit of an imbalance again across the other threads. So we can see here that based on the work they were doing, there was more work done by a couple of the threads, less work done or work that was able to be completed faster by the subsequent threads at the bottom here. If I look at the barrier synchronization time, which is an OpenMP implicit barrier, then I see the waiting time at the barrier synchronizations. And in this case, we see the barrier synchronization values are higher, they're redder, and there's very low waiting times, blues and light blues for the top two ranks. So that's, again, a reflection of the load imbalance, where processes have more time in computation. I'm doing a right click here, a shift click here to select both of them together. Everything together is balanced, but if I just look at the waiting time or just look at the computation time, those are complements of each other. And by adding both of those two together, I end up with something that is uniformly balanced, but allows me to distinguish the computation time from the waiting time. And for the other ranks, I would see a similar pattern, where there's computation time, an overload on some of the threads that is complemented by higher waiting times for the other threads. And then at the end, when we add them both together, we end up with something that is much more balanced. I'll do the same thing in the statistics presentation. In the statistics view, everything looks balanced. If I'm looking at the entire loop, if I look at the computational part, I see a range of values between 2.5 and 3.2 seconds. If I look at the waiting times, I see a variation there between close to 0 and 0.7 seconds. So there's the variation of times, the imbalance in those times shows up in the distribution of values in the statistics. It shows up in the sunburst presentation. It shows up in the topological presentation, and of course, it shows up in the system tree where all of the values are shown in detail. So I think that's shown you some of the waiting time metrics that the trace analysis produced. Let me quickly show some of the other metrics here. I don't want to go through all of them in detail, but the critical path is one which is potentially interesting. So if we were to look at the critical path here, it's saying that the critical path execution is 12.4 seconds roughly. That will correspond to the execution time of the slowest process. So I need to get back to absolute mode here. Here, all of the processes are taking roughly 12 or so seconds. And this is just for the iteration, but if I look at the entire execution, I'll have something that's closer to 12.4. So here the critical path is everything between the MPI init and the MPI finalize. So that's why it's a little bit different from what we're seeing for the individual threads and individual processes. Of that critical path time and where that critical path time is spent, most of it is in the iterative solve, which is what we're interested in, and we can see how that corresponds to the different phases of the solver. How much of it's in the exchange, how much of it's in the X, Y, and Z solve, and how much of it is for the constituent parts of the do loops as well. it's not usually so insightful to look at what's happening at the thread level or even the process level for the critical path. As I said, the critical path will typically move around. In this application, because it's SPMD, all the processes are executing much the same the same computation, and so which process happens to be the last one reaching the barrier, or which thread is reaching the barrier last, is going to be typically varying from execution to execution. But it's already indicating that one of the threads here has a higher amount of time on rank 2, and we would actually see that as imbalance time. So the imbalance time is the part of the critical path that has been flagged as additional computation on one or other threads, one or other processes, and that's the fraction of the critical path that could hopefully be optimized away by balancing things perfectly. Assuming you do that without introducing any additional overheads, you would end up with something that's much closer to the critical path. Here, all of the threads are doing the same operation. The main way to balancing here would likely be to use a more dynamic schedule rather than a static schedule for these parallel regions. But that's a detail for optimization here. Here we're just seeing the potential that could be gained by optimizing the time in those parts of the computation. The delay costs are again showing which parts of the computation are taking most of the time here. Again, it's reflecting the fact that most of the computation is in these do loops here. Those are the parts where you'd have the most potential advantage to balancing things by reducing the costs. At the moment, it's relatively small amounts of MPI delay costs that are, in this case, I'll expand a bit further here, further down. So we have immediate short-term delay costs resulting from the MPI communication, which is up here in the exchange. And then we have longer-term costs, which are as a result of interactions with those processes as the simulation proceeds. So short-term are the immediate costs from immediate interactions, and then the longer-term ones are the ones that propagate and are going from process to process as one is held back by its neighbors, the ones that it's interacting with. On the OpenMP side, the waiting time at the barriers is related to the preceding computation inside the do loops. So again, it's identifying that the do loops are here, the things that need to be balanced, executed more efficiently to eliminate that waiting time at the barriers. Short term and long term are the same as direct and indirect, yes. And these should be explained a little bit more in the online documentation when you bring that up, looking at the explanations of those various costs. So I believe we've been going long enough that it's a good time to take a break. If there are questions, I'll take a look at those and we can try and answer them after the break, or we'll then continue with Christian's presentation. Let me just check that I didn't miss anything on the slides here, because I think that that should have been enough for you to be able to get the trace analysis, to see that the trace analysis was done immediately after the measurement completed. If you get warnings about message violations, that's an indication that where you have done measurement across multiple nodes, in different nodes, the timestamps are not synchronized across the nodes, which is why you might need to use this time correction. I showed it in the job script for, it's not on the slides here, but it was in the job script. Time correction is usually not needed on a single rank, a single node, but if you're running across multiple nodes, then I think it's typically necessary and valuable. Without having the timestamps being adjusted to be synchronized across the ranks, you would end up with potentially distorted analyses. And then we looked at the additional metrics that show up in the analysis report. And the additional descriptions of those, the critical path analysis, we look at the imbalance on the critical path. So there's all sorts of other statistics there, but I don't think we need to go through those for the moment. So at this point, I will say we'll take a break. That break, I think, could be 20 minutes. 30, yeah. I think we can have a 20-minute break, but we can answer questions while we're in that break, and then we'll continue with Jen's presentation, where we can see more things that you can do with SCORE-P, more things that can be included in the measurements and corresponding analyses. They're not necessarily related to tracing, but they're part of the extended SCORE-P presentation. How much memory does Cube require to process 1 gigabyte of profile data? If there's a gigabyte of profile data, then I would expect that Cube would try and store that in memory, so at least a gigabyte. But since the profile data is potentially compressed, expanding it might require 10 gigabytes or more. It's hard to predict. I think that's something you'd have to do by trial and error. I don't think there's any. You can expect it to need more memory, but how much more memory, I think, is not something that we can pinpoint at this point. So Dale has asked to clarify the user commands that we're seeing here, the user instrumentation we're seeing here. We'll see how to do it more precisely in the slides that Christian will present, but the reason to do it was to be able to distinguish the timed part of this application benchmark from the initialization. So that's why we annotated the loop of the main do loop, in this case, of the application to mark it, just so we can distinguish the time that's reported by the benchmark with the time that we measure and record in SCORE-P. So this is the code here. You can look at the code in the directory. It's in the file that's provided. This is the main benchmark loop. It says here, benchmark time step loop. This is the do loop itself. Here we see where the timer of the application is used to start and stop it. So this is the part that we would really like to distinguish from everything else. Everything else is initialization, verification at the end. It's not so valuable for our analysis. So if that's the case, then we can mark the part that we're interested in. What we've done here is to put the markers inside the do loop itself. In principle, the markers could have been outside the do loop, and then we would see the time for the do loop as a whole, or all of the iterations would be aggregated together. The advantage of having the the markers inside the do loop is so that I can see how many times the do loop is executed. So if I look at the visit counts for here for the iteration, it's telling me it's executed 1,600 times, and that is 200 times by each process. That's the benchmark configuration. So I see that iterative region inside the do loop is executed 200 times by each rank, which is what I expect. The routines here, executed 200 times within that region, are also executed as part of the initialization, but they're only executed once as part of the initialization. So the first time, often there's some caching effects. The first time the data is accessed, they can be a little bit slower. They may not be representative. They are typically not what you would want to include in your benchmark timing. So that's why the application itself executes these routines once, and then it has a barrier before it continues with the timed part of the execution. So by putting the marker in here, I can readily do that distinction. And to enable that marker is why I would then use the scorp-user option. There's lots of other scorp instrumentation options. Christian will show you a few of them, but the one for enabling user instrumentation is the one that I was demonstrating, or we're demonstrating with this example here. The user instrumentation, user annotations are also used for to disable measurement for parts that are not relevant, that are parts that are not so interesting. So here in the source code, we also had a part of the initialization that I just arbitrarily said I don't want to collect any measurement details for. So that's why after the MPI setup, I put in the marker to say stop recording at that point. And until it comes to the next recording on, which is down here, everything that's inside this region would not be included. So there's all sorts of setup routines here that I could have included in the profile. There'd be no great challenge with including it in the profile, but I just don't need them, and I don't need them in the trace. So that's why I said recording off for that phase of execution. If I wanted to be a little bit more clever, I could have said I just wanted to collect the odd iterations or the iterations after iteration 50, and then I could have programmatically said if iteration is greater than 50, start recording at that point and disable recording at the end. So by providing these macros, which are part of the Scorp API, you have much more control over which regions, which phases of execution are included in the measurement and which ones are not. It's not as convenient, it's not the same as filtering, but the end result is more or less the same. Once something has been filtered, it doesn't appear in the measurement. In this case, once you're in a region where measurement is disabled, then the details of what's happening in that measurement won't be included in the resulting profile or the resulting trace. Yes, so if I didn't have the iteration here, what I would have seen in the measurement, and you can verify this yourself, is see that the exchange QBC is executed not 200 times plus 1 time, but you'd see that it's actually executed 201 times. But by putting in the markers, I can then distinguish the one that I'm not interested in from the 200, which I am.
Hi, can I ask a question?
Sure, go ahead.
Actually, I asked that 2 days ago, but I didn't really understand it. You said that we can do this POP metrics, right, with the Scalasca and Scorp. We saw if we want to do the scalability analysis and to measure eventually the metrics from POP to have the efficiency of the code and all that stuff. So what's the idea that I should do? So first I need to run it for many cases, right? And then how can I incorporate all this information with Scalasca and get the metrics?
Okay, so I mean, I just have an arbitrary measurement here, which is actually I just rebuilt and reran the benchmark example without the user instrumentation. So just to demonstrate what we were previously talking about, here we have the ADI executed what I believe is not the ADI. Here we're seeing how often ADI is executed rather than how often the these two routines, exchange and ADI, are now no longer distinguished between the initialization and the iterative part, which was marked. Also, these setup routines, which I had in the recording off, as well as the broadcast here, those now show up in the profile as well. So by comparing this measurement with the one where we had the user instrumentation, the differences are that I think everything here was part of the recording off, and the first instance, the first execution of those routines was part of the initialization. It was outside of the do loop, and then the subsequent ones after the timer start were then part of the iteration. So we could distinguish what was the key part of the measurement from the other part. That's valuable for different reasons, and it's also valuable in the context of the POP metrics, which I didn't discuss in detail, but I can briefly mention now. The ADI is where most of the time is spent. That's our benchmark. That's the part that's timed. Here we're seeing also the time that it's called for the first initialization. We can't distinguish that in the profile. A lot of the other time is in this exchange QBC. So this is now 99% of the total execution time. So there's not a big difference between selecting both of those and selecting the entire application. In the general panel here on the right-hand side is where we have the POP efficiency metrics in various varieties. And so those can be calculated when demand for whatever call path is selected. It doesn't matter which metrics you have selected here on the left-hand side, but it does matter which metrics are in the measurement, which are in the file here. So that's why you're not seeing serialization and summary transfer efficiency here, because those are only available from trace analysis. Things like IPC are also only available if we collect hardware counters. But for the metrics that it's able to calculate, those are what you're now seeing here. So it's showing you the load balance efficiency, which is the ratio of time between the mean and the maximum computation. The communication efficiency is the ratio between the computation time and the total runtime, the maximum computation time and the total runtime of an individual process. So those metrics are calculated and available on demand. They can be calculated for the entire execution. They can be calculated just for a subset of the execution. If I was to calculate them just for the exchange QBC, I would see that's where most of the communication is done, and therefore that is considered much less efficient than the overall execution. The ADI is where most of the computation is, so it probably won't look very different to the overall execution. But the metrics here are only calculated where that information is available. We'll see in a moment how to add hardware counters, and you already saw the trace analysis. So if I close this one and look at the previous trace measurement that we did, this will also open on my screen. Yes, here.
Sorry, can I interrupt for a minute?
Sure.
The metrics that you show us, the efficiency, is only for one case, right? So you run the case for eight CPUs or 8 processes, and this is what we saw here. This is okay.
You only get the efficiencies for the case that is being examined. Yes.
can I get an efficiency like if I run the same case but with different processors, like from 8, then 16, then 32, and then scale up? Can I get these indices or these metrics for this case, or
you will
no?
get these metrics for each case.
For each
you will
case,
not get the scaling. You will not get the scaling efficiency because currently that's not provided by Cube, or that's something that we calculate separately.
Okay.
Maybe in the future we'll be able to include the scaling efficiencies as well for multiple measurements, but at the moment we only give you the efficiencies for each individual measurement, and the efficiencies you get depend on what's in that measurement. So if it's a trace measurement like we have here, then you get the efficiencies which are possible to be calculated from that based on the waiting times.
Okay, I see.
In a summary which doesn't have the waiting times, you don't get some of these metrics. For things like IPC, we need to include the hardware counters that are for instructions and cycles, and those are they're shown in the job script, but we didn't do a run with them yet. So here, where it says PAPI metrics equals total instructions, total cycles, those are the ones you need to get IPC, instructions per cycle.
Okay, thank you.
So once you understand how to do some basic measurements, we'll continue in a moment and show you how to augment those to get the additional information that you might be interested in.
Yeah, sure.
Christian, are you ready to continue?
And one last question, just to be sure. I mean, I want to do this analysis to take the measurements and take the pop metrics. I guess because I have a CFD code, a computational fluid dynamics code, and I guess I don't need to run it for many time steps, right? I don't need to run my code for many time steps, right? Only a few hundreds, probably it's enough to get all the metrics.
What you should do is you should configure your code to run and for a period of time where you have a stable or consistent execution. So as I mentioned, typically the first iteration or the first few iterations, depending on what you're doing, may not be representative of the others.
Yeah, true.
So if you're lucky, you just trace the first one and you're done. You just need to run that and analyze it. But if you have differences between the first iteration or the first time step and then the subsequent ones, then you probably either want to avoid the first one or the first few and just do recording on, recording off for the ones that you're interested in. Or you have to make sure that your total execution is long enough that it's not biased by the first one, which is not representative. So if the first one is only a few % different, then you can probably get away with doing 10 time steps. Maybe you need 100. If it's varying from time step to time step, you will need a larger number of iterations anyway. So it's not uncommon to need 100 or maybe 1,000. I mean, we understand that if you're running for days and days, it's quite conceivable that your simulation performance is changing as the data is evolving, as you have shock fronts, as you have, I don't know, other characteristics that are happening, not necessarily at every time step, or that are growing and spreading out through your simulation domain. So either you have a longer profile that has everything aggregated together, or you would have to split that into separate profiles where you're looking at each phase of execution, the first few hundred time steps, and then some 100 time steps closer to the end. And if they're very similar, then great, you don't have to worry about the differences. But if you have a simulation that's changing with time, then you probably need to be a bit careful about how representative the time steps you're looking at are of the greater or the longer execution.
Yeah, true. I did a test to see the influence of the initial conditions. Let's say if we start from the initial conditions, and then if we restart from a stable solution, as you said, and the difference in the wall time, it's close to 15 or 16%. So yeah, it is true.
So the first iterations are 15% slower than once you're in a steady state.
15% slower, yeah. But I tested only with 100 time steps, not many, because it's very time consuming to do for many. Yeah.
There are ways of getting a profile per time step, but if you end up with 1,000 time steps and 1,000 profiles, that will also not be very manageable. If you're looking at an execution trace, it's much easier to just ignore the first part and zoom into a few iterations that are later on. But we're not covering Vampire in this workshop because it's not installed and available on Archer. So there we're more constrained with how to limit the analysis to a subset of the timeline, a subset of the execution time.
Yeah. I realized that it is super difficult to compare codes and efficiencies of the codes until let's say that this code is efficient, or they say, okay, with these tools we can make it more efficient. But when in terms of comparisons, then it's difficult to make comparisons between codes in terms of scalability.
Yes, I mean, each code will have its own characteristics in terms of how it's using MPI, how it's using threading, how much data it's accessing from cache or from memory, how many floating point operations it's doing. All of those are very application specific. So that's why the efficiencies that POP presents are rather more abstract, and they can apply to a variety of codes without saying specifically that you have an MPI synchronization problem or you have a problem with memory access. That would be the next step of the analysis. The POP metrics allow you to compare the efficiencies between codes relatively easily, but they don't give you the detailed information that you would need to be able to optimize. They tell you where to look, what efficiencies to look at, but what things need to be optimized is, again, at the next level down, that is application specific and compiler specific and processor specific.
Okay, sorry if I if I consumed more of the time. Okay, sorry. Thank you very much.
Christian, are you ready to continue?
Yes. Okay, let's.
I think that your presentation will probably take us close to the lunchtime, which is, well, now it's in 50 minutes, but let's see how much time we have. But I mean, it's much better to spend time answering questions than to present things which are not relevant or not so interesting. Are you going to grab the screen, or do you need me to release it?
Yes, so I already started it. Yeah, okay.
Okay.
So maybe we come back to what was already presented on Tuesday. So we had two ways to instrument your code. One way was to use the scorp command with some options in front of your compiler. This usually works if you have just a makefile and you can modify the makefile. If you have build systems like CMake, where is mine here? CMake or Auto Tools, or what we had on Tuesday was genmake, then this usually doesn't work. So therefore, we provide additional compiler wrappers for each installation. So for example, here on Archer, we have the Scorpy CC, Scorpy capital CC, and the FTN for C, C++, and Fortran. And these then need to be introduced into your build system. So in the CMake case, you do it like this. Here you tell CMake that Scorpy ICC would be the the C compiler, and the same here for C++. And then you run CMake or configure in the AutoTools context, or genmake. But during this configuration step, Scorpy shouldn't be active, so it shouldn't do any measurements, shouldn't create any experiment directories. So therefore, we can switch it off using the Scorpy_wrapper environment variable. So so once the configure step is done, you usually just call make, and then the question is, how can Scorpy options or additional compiler options be introduced in this make step? So, and here again, we use some environment variables. So this -- user flag that we have seen several times would then go into this Scorpy wrapper instrumenter flags variable, and additional compiler flags like -f openmp would go into Scorpy wrapper compiler flags. So just as a recap, to get the instrumentation step done. But I
Christian,
think, yes, yeah.
the fopenmp
Yes.
is going to be part of the normal compiler flags, so you don't add it.
Yes, yes. In this, yeah. This was just an example. If you want to add some special flags, then you could use this variable. But yeah, in most cases, you don't need additional flags. I think we introduced this this variable because with the OpenMP instrumentation using Opari, we in some compilers we needed additional compiler flags, which can be looked up in the open issues file. I think this was the reason. But usually you just need the Scorpy wrapper instrumenter flags.
And you don't add flags which the application needs. So if you need OpenMP, if you need AVX 512 or whatever, those are part of the normal application flags that would not go here.
Yeah. We only need this if Scorpy breaks something, which happens in really rare cases, and then it's documented in the open issues file. Okay, so on Tuesday we had several breakout sessions, and I think there were several people being able to instrument the codes with Scorpy, which I think it's a great success. And now once the application is instrumented, we can do several measurements. And as already told on Tuesday, so the measurements are being configured using environment variables. So and the list of all environment variables can be seen with the Scorpy info command. Then I put the config vars here, or maybe just the help. So usually all the Scorpy and Scalasca commands come with the --help. So and here we see that with the config vars subcommand, we see a list of all config variables. And when we add the -- full here, then we get more detailed information. And this is usually specific to the installation. So if your installation here has no CUDA support, then you won't see any CUDA flags, which is the case here on Archer. So yeah, so this here you see then the list of the environment variables. So for example, the profiling one that we use basically always, it defaults to true. Then the very important one is the tracing that is then set by the scan command automatically. So it defaults to false. As we first start with a profile measurement, do the scoring, adjust or potentially create a filter file, which is then activated using the Scorpy filtering file environment variable, and with this we can set up a trace experiment, which also would need, I think, the Scorpy total memory, which was described somewhere in the beginning. Yeah, here the Scorpy total memory. So yeah, here you can see with the Scorpy info command, you can see the list of all available environment variables. So most of, or several of them are not very, or not so interesting. So for example, the Scorpy page size usually stays at the default, and you don't need to care about this. Okay, so I now want to highlight some of these environment variables. So for example, here this memory usage environment variable. So if this is set to true, this copy memory recording or MPI memory recording, then we intercept calls to malloc, calloc, realloc, free, new, and delete. So this usually works for C and C++. For Fortran, it only works with the GNU compilers, as the GNU compiler then maps to the C allocation functions. Yeah, similar for MPI. There's also, I think, some version for shmem if your application, or if the Scorpy installation supports shmem, then you can switch this on and get some additional information. So it will then look like this here. So you get some maximum heap memory allocated. So basically, yeah, upper value of the memory allocated at a time. And you can also then see where memory was leaked. So we intercept all the malloc calls. And if there's not a corresponding free, we will mark the allocations that don't have a corresponding free if you select the bytes leaked metric here. So then we talked about PAPI counters several times, or hardware counters in general. So these are introduced by the environment variable Scorpy metric PAPI, or Scorpy metric PAPI per process. So this per process are only collected for the master, or for the master thread of each rank. And the other ones are collected for each thread. And the counters are collected for every enter and for every exit of the functions. And then we take the difference of these two values. To see which counters are available, there is this puppy avail command, and there are you can choose between different counters. Not all of them can be used together, and I think we also in Scorpy support only a limited number of counters. We also noted that sometimes reading these counters for every enter and exit might create some significant overhead, but this depends a little bit on the CPU you're using. You can only query metrics from Linux perf. It's basically the same, just the name of the variable changes. It's Scorpy metric perf or Scorpy metric perf per process. And with perf list, you get a list of potential available counters. Another option would be to write your own metric plugin. So for example, if you have some specialized hardware and an API to query this hardware, then you could create a plugin to query this special hardware for every enter and exit event. There are some plugins available at this repository that can serve as an example. So now we come to the Scorpy user instrumentation API. So we already, or Brian already showed examples in the VT code. So this can be used either to partition your initialization from solver A, solver B, and so on. But you can also subdivide some large functions, so some spaghetti code to get a little bit more structure into these large functions. To enable the user instrumentation, you need to specify the --user flag while you are instrumenting. We saw this several times already today and on Tuesday. So this is available for all the 3 languages that we support. And now we have some examples here. So we always need to include some include file, and this differs for C, C++, and Fortran. Then we usually have a definition of a region. So Scorpy user region define with some name here, or some. This will be transformed into a variable. And then we have, after the definition, we have a begin and an end. So here we take then the begin timestamp, the end timestamp, potentially hardware counters, and everything in between will then in a call tree be under this this region, which is called then solver. So here you at the begin you give it a name and some specific type. Then for C and C++, it's similar. So the include file differs a little bit. It's called scorpyuser.h, but you still have the same way to define the region here, and the same way to begin to mark the region begin and the region end. For C++, then there is something special, because for C++, we can make use of constructors and destructors. and automatic variables. So the Scorpy user region begin here. So in contrast to the other two options here, we just have a single invocation of a Scorpy macro. We call a constructor here of a specific class, and this constructor will create then this local variable that we need. It will do the enter call, and then here at the end of the block, the destructor is called automatically. So this is guaranteed by the C++ standard. So here we have the enter, and here we have or the begin, and here we have the end of the region. So it, yeah, it's a little bit more convenient than having three macros to use. Then there is the Scorpy measurement control API, where you can deactivate and reactivate the recording. So which was already shown by Brian with the VT example. So you have this Scorpy recording off macro. So it's the same in Fortran and C++. And then you have the Scorpy recording on. So everything between recording off and recording on. There you will not get any additional region enter and exit, even if they might be instrumented. But you will get a new measurement off region in the call tree that will then have the the inclusive time of everything which happens here in this loop. You need to make sure that you use these macros in a serial context. So it's usually a bad idea if you do this within an OpenMP parallel region or in a pthread. And you might then, or the measurement might abort then. Okay, so coming back from the instrumentation to some measurement configuration using environment variables. So we are able to intercept some or to get some information from CUDA applications using the kubectl library, which is provided by NVIDIA with every CUDA installation. And there we can measure different different activities on the devices, which are then specified using this Scorpy CUDA enable environment variable. Same is true for OpenCL and also for OpenACC. And again, if you have a Scorpy installation which supports CUDA, OpenACC, or OpenCL, check the Scorpy info command to get a list of and some documentation about what is possible to specify there. So any plans to support HIP was a question in the chat. Yes, we have a development branch for HIP. And this, I think, will might appear at the end of the year in a product. It's usually it's possible if so to also get access to some development version. So as our colleagues in Dresden are developing this the HIP feature, I'm not sure about the current status of this branch. But you can send an email to Scorpy support, and if you want to be early tester, and if you're willing to provide some feedback. Okay, so here is then what it might look like if you have an application that uses some GPU devices. So you have the thread here on the CPU, and then you have an extra location. Oh, okay, maybe so I should introduce this this view here. So this is a screenshot of Vampire. So Vampire is a tool that is able to analyze some trace data. So usually showing a tracing timeline. So for example, what you see here is the master thread. And you see here different functions the master thread is calling, or different groups of functions which are color coded. So for example, here this purple one is some OpenACC, which you see here. And then there are some CUDA API functions classified here. And then these lines here are some host device memory transfers. So here, this is the CPU timeline, and here is the GPU timeline. And for the GPU timeline, we get some device activities using this kubectl library. And I think this here was also an application that uses OpenACC, and OpenACC translated to some CUDA API calls underneath, which you can see here in this in this view here. So this is basically something like a call tree. You see main, and main calls this reuse at OpenACC kernel. And then you get some OpenACC function here, which calls some other OpenACC functions, which then calls some CUDA stuff here. Okay, then sometimes the overhead for C++ applications becomes quite high. So this depends on the compiler and the way the filtering is done. There's one compiler that instruments all inline functions, which is usually not what you want. So this is the Intel compiler. So usually inline functions are quite small, and they don't consume much time. So the relative overhead of instrumenting these functions is quite high. Therefore, most of the compilers don't instrument inline functions, or can be configured that they don't instrument inline functions. So yeah, but sometimes, especially for for Intel, the overhead is quite high. We from the version 7 from Scorpion, we have the way of compile time filter these functions, which I think works quite well. But we also have the an option to do some sampling instead of this compiler-based instrumentation. So we still generate or we still intercept this MPI, this OpenMP calls, but we don't have this function enter exit for all the user code. But from time to time, we interrupt the measurement. We look at the call stack, and we walk the call stack up to main, and then create some statistical information that we then combine with the correct timings of the MPI and OpenMP. This is still a little bit experimental, and if you can I would suggest or advise to use the instrumentation and provide some runtime filter, or if necessary, also some compile time filter, instead of using the sampling one. Especially with OpenMP, we know that there are some issues that are not easily being fixed. But in this example here, you see that with the sampling activated, so this again is a vampire screenshot, you reduce the overhead by quite some significant amount. Then also a topic that was briefly discussed on Tuesday is wrapping third-party libraries that are installed on your system or that you need to install for your application. For example, if your application uses FFTW, you're not an FFTW developer, so you don't really know what's going inside this library, and you maybe also don't really care, because even if you find a bottleneck there, if you're not the developer, you might not be able to fix this, but you still want to see where your application calls this FFTW API functions. We can, if we have a header file for this FFTW or any other C or C++ based library, we can create wrappers for these library API calls. This is complex, or you have to at least have to do several steps once to create this wrapper, to install the wrapper. But once this is done, you can use it quite often for every application that that uses this external library. So I will not go into detail how to install the wrapper. Here is some details how to do this, but just show you a vampire screenshot again. So here the calls to FFTW, here marked in purple, are wrapped, and you see directly that FFTW is usually used here in the beginning on the master thread of each of the ranks. And with this, you can at a glance see how much time your external library is consuming and where it is called. So there is, I think, also a POP article here, which describes how to set up such a wrapper. I will put this into the chat. So for anyone who's interested. Okay, that was the last of my slides. So here are some contact information. So if you have any questions, just send an email to this support@scorp.org address. And yeah, if you have some additional questions to this advanced measurement capabilities, so please ask now or also this afternoon. Otherwise, I would now hand back to Brian. Brian, are you going to show some of the case studies now? Or?
Christian, one sec.
Yes. Yeah.
Is there? So there was a question how to load this Scorp plugins, Scorp metric plugins. Does one need to recompile Scorp or only plugin and so on?
Yeah, you need to create the plugin, and once you have a plugin, I think you can use it using an environment variable. Here, this Scorpy metric plugins. Yeah, you can provide a list of plugins, and plugins need to be shared objects. And when you build a plugin, you need to have a Scorpy installation, and you need to access some Scorpy headers. This is described somewhere. I will look it up and I will paste the documentation here in the chat. So, but yeah, building the plugin and then using the plugin are two distinct jobs. So building it, usually it's just a single C file, or usually you can put, yeah, it depends on the plugin, but quite often the ones found at GitHub are just a few lines of code. You build it as a shared object, and then you can use it using this environment variable.
Okay.
So Brian, are you going to continue with the case studies?
Yes, if there's no more questions, then I would go back to that. So just to pick up on a few things that we didn't cover, a lot of the other utilities that Cube provides. So if you run the Cube and the Cube tab command, then there's different command line utilities that are available for working with Cube files. So there's ones for merging files together, which you can use to combine different hardware counter measurements, for example, or there's ones for doing differences between two measurements. And the outcome of one of those, what we call algebra utilities, is a new Cube file where you get a call path by call path, metric by metric calculation of the differences or the sum of those different metrics. So those are installed and available to experiment with. There's more documentation about Cube on the Scalasca website, as well as the Scalasca as well. So that's the summary slide here. And I just wanted to take the last few minutes to look at one or two case studies that we have used the tools with. So one of those, one of the codes we've worked with is a code called HEMLB, which is a lattice-Boltzmann solver, part of the CompBiomed Center of Excellence for Computational Biomedicine. There we did an analysis of it, looking at its scalability on the SuperMOOC NG system. So it's Skylake processors, dual Skylake processor nodes, and we were able to do measurements with Scorpy up to more or less the full scale of the machine. So with roughly 6,500 compute nodes or 300,000 MPI processes. It's a C++ code using MPI. There's also a version that uses CUDA, but here we're just looking at the MPI version built with the Intel compilers and Intel MPI library. And one of the interesting characteristics of the application was that there's a subset of the processes that are used for reading in and distributing the data. And then once the data has been distributed, the simulation is actually done by not all of the others, but by all but one of the others. So there's, again, another dedicated process that is used for monitoring the status of the simulation. The data set used for this analysis was the circle Willis geometry, which is part of the arterial network in the brain, the human brain here. And the simulation was run for roughly, for 5,000 time steps, which is roughly 500 microseconds. The high resolution data set was over 20 gigabytes, corresponding to 10,000 million lattice sites. So quite a large high resolution data set of a very complex geometry, and one that's suitable for this lattice-Boltzmann method that can handle these complex geometries and the blood flow within them. These graphs are showing the measurements that we were able to take from the application, looking at the strong scaling of the simulation part. So the total time flattened off, but the simulation part was scaling relatively well, from the smallest configuration where we could actually run using larger memory nodes down to here where we're dealing with something close to the full number of nodes of the machine. And this was able to provide a 190-fold speed up of the simulation compared with the smallest configuration. So from 18 nodes up to 6,480 nodes, we got a 190-fold speed up for the simulation phase. I haven't really gone into detail here, but as part of the Center of Excellence for Performance Optimization and Productivity, we developed a number of efficiency metrics. And those efficiency metrics are also those which you can obtain within the Cube GUI. And I presented that in the break, but hopefully you got an insight into how you can get those metrics. Here, we're looking at two aspects. One is the efficiency metrics that are calculated for each execution configuration, and then we're seeing how things change as you scale up and do measurements with different sizes. With our first, with the smallest execution configurations, we are using those as a reference for the latter ones. So that's why some of the metrics, the computation metrics, for the smallest configuration are defined to be one. And the other metrics which are calculated, the efficiency metrics, we're identifying load imbalance as something that even for this, what we would call relatively small configuration of 1,100 processes, load balance was still an issue here. Load imbalance is defined as the ratio of the mean computation time to the maximum process computation time. And so that was something that was relatively stable, but it was up and down as we changed the scale. Sometimes it got a little bit higher, sometimes a little bit lower. That's very much depending on how this complex geometry is partitioned and distributed across the machine. It never gets too bad, but it's also something there where there's roughly 20 to 30% could be gained by optimizing things and having a perfect load balance efficiency. Not easy to do by any means, but the headroom is there, and that's what the efficiency metric is characterizing. For the communication efficiency, that starts off very good. The application is using non-blocking communication and only communicating with a limited number of neighbors, but that efficiency also is one that starts dropping off with scale. It never gets particularly low, so even at the very largest scale of 300,000 processes, it's still not a big issue. But what we were seeing as a scaling limitation at the largest scale was the computation scaling, that as we got to very largest scales, the computation scaling, the amount of time used for the purely computational parts was growing in a way that manifests itself as impacting on the efficiency here. And the reason for that is explained in the subsequent metrics, which are looking at IPC and instruction scaling. On the IPC side, the computations were actually getting more efficient. As the computation of the work that was to be done by each node got smaller, it involved less memory accesses, it fitted better into cache, and therefore the instructions per cycle got better, and therefore there was a benefit at larger scales. Unfortunately, as the computational domains that each process was dealing with got smaller, you're then dealing with more boundary issues with packing messages and unpacking things for communication and distribution to neighbors. So there is where we're seeing the biggest impact in terms of a diminishing of the scaling efficiency, which is only partially compensated by the fact that the cache utilization is better and you get the increased IPC. The reference case here was just the smallest configuration that could be run on the system. So given that it was needing a large amount of memory, we couldn't run it on a single node. We couldn't even run it on less than 24 nodes. And that's why here we're seeing the values calculated for the smallest runnable configuration where the data fitted in memory. The other thing that is to note is that there's a gap here between the smaller numbers and the larger ones. The smaller ones were using large memory nodes. The larger configurations were using the normal nodes, which didn't have as much memory available. And this intermediate configuration here, there just wasn't enough of the large memory nodes to run it, and there wasn't enough memory to run it on the normal memory nodes. So that's why there's a gap in the scale here. So that's an example of the sorts of metrics that we defined and we use to quantify performance of and compare applications as part of the POP Center of Excellence. There's much more information on the POP COE website here. In terms of what you see in the measurements when you're looking at them with Scalasca here, we're looking at a measurement which is not one of the largest ones, but one of the intermediate sizes. So here we're actually looking at 13,824 processes. I guess that's around 250 nodes, if I remember correctly, each with 48 ranks per process. And when we're looking at, so this was instrumented relatively carefully because it was C++. We were only instrumenting the main computational module, which is where run simulation was taking place. And we disabled measurement for the majority of the initialization. So there's a relatively long, complicated process of reading in the data, distributing it across the nodes, including that in the trace measurements was prohibitive. So that's why for those we mark those and then have measurement disabled for those. So we can focus on seeing the breakdown of time in the run simulation part, and then where the communication is done, which is in this part here, where we see the non-blocking send and receive, and the wait all, which is where those are completed. At the end of each time step, there's a gather operation, and that also is where we're able to see there's an imbalance of the execution time across the processes. The ones which finish the computation and their nearest neighbor communication faster have less waiting time, whereas the ones that have larger waiting times, the ones that have less work to do have longer waiting times in the subsequent gather. Trying to see what's happening on even this number of processes, 13,000 processes is challenging, as I said, in these call tree presentations. So that's why we also use the topological presentation here. In this case, I'm showing all of the processes. The application actually uses a three-dimensional MPI Cartesian topology, but here I'm just breaking things down and looking at the variation across the compute nodes. So we have 48, I believe, in one dimension, and some other number of processes in the other dimension. So it's not strictly representing the application's topology, but it's just a way of showing all of the processes together to get an overview of where values are higher or where they're lower. And one of the things that we identified from the metrics was that a lot of the waiting time was due to just one or two processes taking a lot longer for the computation, and those one or two processes were spending a lot more time in memory stalls. So these are various hardware counters where we had included those in the measurements, and the hardware counter for looking at memory stalls, which is an Intel-specific counter, a Skylake counter, was showing very high values just for one or two processes in this case. And this was something that we were intrigued to find changed from run to run, that it wasn't related to the data that a particular process had. It was something that was a hardware characteristic of the machine that we're running on, or the processor, that depending on how the data is mapped into memory, the physical addresses of that data result in extra memory stalls for some of those data accesses that slow down one or more of the processes. We also, when we were doing some very large-scale measurements using all of the nodes, we had certain nodes where we could identify that all of the processes on that node were slow. So not just one core, not just a few cores, but all of the cores, or most of the cores on a few nodes, were showing much slower performance. And this was tracked down to some problems with the DIMMs, with the hardware memory attached to those nodes. That was something that was static. It didn't change from run to run, so we could just rerun a measurement avoiding those nodes, and then get the scalability that the application was able to exploit. Question I'm trying to read at the moment about being able to aggregate things in the topology views. As far as I know, the topologies are not able to do that yet. As Pavel says, if you can use the sunburst, which won't actually work with 100,000 processes, then you can have some more hierarchical view. But these topologies are defined at the process level or the thread level, and they don't allow you to aggregate values from processes and threads, at the moment at least. So yeah, this was where I'm just showing in the break that if you go into the General tab at the right-hand side, it gives you the Advisor plugin. That Advisor plugin is able to calculate these efficiency metrics for load balance, and depending on what you have in the measurement, it will calculate the efficiencies that are possible for it. So for serialization and transfer time, those are based on the waiting times. For that, we would need to do a trace analysis. This is just a summary measurement with some hardware counters in it. So that's why we don't have those metrics, but we have the other metrics that come from the hardware counters in this case. Another version of this code is a version that was based on some early GPU usage, so using CUDA to use GPUs. So running one MPI process for each GPU on a system. Here we had in Jülich, where there were 4 NVIDIA Volta GPUs per node. We could actually get the measurements for those up to 56 nodes, or at least 32 nodes were included in this measurement. This set of measurements up to 129 processes. So again, one process is a monitor process that wasn't actually involved in the computation. It was just checking how things were proceeding. And then one process per GPU, one process driving each GPU. when we look at the GPU metrics, those appear as additional streams in the topology on the right-hand side. So here we have 6 or 7 additional CUDA streams for each of the nodes, each of the processes that was driving a GPU. And the GPU kernels, the CUDA kernels, appear as a separate hierarchy. So those are executed asynchronously from the CPU computation. That's why they're shown in a separate hierarchy here. Actually, I think in the new versions of SCORP, there's a new tab where they're shown separately from the GPU from the CPU metrics, the CPU call tree. But basically, we can get a breakdown of which kernels are executed, how much time is executed on each GPU for them, and here we're seeing it in the numerical form. It's also possible to combine those into topological form, where although it says process time stream, this is the processes, 128 to 129 processes in the vertical dimension, and then the 8 to 10, however many streams there were in the horizontal dimension. The rank at the top, I hope you can see, wasn't using a GPU at all, which wasn't a problem. And then the GPUs are used to execute different streams on the different GPUs. We also see by the coloring here that some of the GPUs are only executed on a subset of some of the kernels are only executed on a subset of the GPUs, others are executed on all of them. So both of those were factors in some of the load balance that we were seeing for this application. Here is another example where we're selecting the MPI file I/O time. So here at the end of the simulation, or periodically throughout the simulation actually, it was writing state files. It was using an MPI file write operation to write them. That is only used by the master processes, so it's not, of course, writing from the GPUs. But we also see that writing time is something that varies considerably across the MPI ranks. So there's although they are writing close to the same amount of information, although I think there's some variation, there are additional metrics provided in terms of the bytes written in red here. But it is varying across the ranks, and of course the writing time is also a major factor in the overall load balance of this application, as it's periodically writing these state files after every 500 or every 1,000 time steps, or however it was configured. The other thing that we could see imbalanced across the GPUs in this case was the way in which they were transferring data to and from the GPUs. So where we look at the memory copies, which were in this case asynchronous memory copies, the time for those was also predominantly for a few GPUs, a few MPI ranks in the middle of the computational domain. This again was a characteristic of the data set that was being used, how it was partitioned and distributed across the MPI rank. It meant that there was extra work allocated to a few of the processes. They happened to be the processes that were in the middle of the computational domain and therefore in the middle of the set of processes. And that data transfer time was again additional cause of the imbalance here, and another cause of imbalance across the processes and threads. Here on the right-hand side, we're seeing, in addition to the MPI metrics that we discussed previously, the aggregate CUDA metrics, so the time for launching the kernels, for doing synchronization, and also for, in this case, what's highlighted as memory management, memory copies. So those are all GPU-specific metrics that only relate to applications which are measured in using GPUs, or using CUDA in this case. The application was actually scaling relatively well on the CPU side, which are the dashed lines here, or the hollow circles. Where things were not so efficient was where it was doing file I/O, and then those are tailing off at the larger scale here. That was the biggest bottleneck, but there was also a bottleneck in the communication that was done as well. So there was no there was extra data transfers related to getting the data off of the GPUs and then transferring it between the MPI nodes, and that's why that's the other thing that affected the ability to scale, in this case up to 32 nodes as opposed to just 16 nodes. So all of those are manifested and summarized in the efficiency metrics that I mentioned. Again, here we're just looking at the GPU efficiency. We're using the smallest configuration on a single node as the reference case. The computation scaling is not great, but it's not bad. The load balance is something that becomes a dominating deficiency here. On a single node, the load balance is pretty good, but even with 2 nodes, 4 nodes, it's starting to deteriorate significantly, and with only 32 nodes, it's already very inefficient here, very imbalanced. Communication inefficiencies are actually not great even for the smallest single configuration. So here, communication efficiency relates to getting the data off the GPUs and then transferring it between the processes on that node. It's already low on a single node and getting worse as it goes to higher numbers of nodes. So this was an early version of the code, the first version that we were able to run up to 32 nodes here. A lot of these deficiencies have already been addressed. They've been run now, or code has been run now with on the Summit system in the US at Oak Ridge. I think it's been run with 1,000 nodes now with much better efficiency. But this was the way in which the code was, the state at which it was when we analyzed it earlier. So yeah, this is a breakdown of the different metrics that we were able to calculate, comparing the different configurations running from 1 to 32 nodes, and comparing what's happening on the CPU side versus the GPU side. So the right-hand bars are the GPUs. We see that the computation time on the GPUs is increasing, so that's one inefficiency, but it's not too bad. For strong scaling, these bars should be the same height. The fact that it increases is not great, but the main inefficiency is the fact that what's happening on the CPU side. Getting the data from the GPU, transferring it between CPUs, and then getting it back into the other GPUs is being caught in the MPI communication time here, as well as the synchronization time, the CUDA synchronization and memory copy time for CUDA here. So all of those overheads, all of those times are increasing with scale. And then at the very largest configurations, we also have the MPI file I/O. So file I/O was a big issue for the largest scale configurations here. And because the CPUs were being held up by this, that meant that a lot of the time was idle time on the GPU side. So that's the part outlined in red here is the difference between the two bars, which is then corresponding to idle time on the GPU side, which is growing and not great. Okay, so I don't think I want to take more time here. This is as far as I think we wanted to cover things this morning, with taking us up to the lunch break. I'm already conscious that we're in the lunch break time. We will have time this afternoon. In roughly an hour's time, we will be back to help you with your own application codes to continue the work that was started on Tuesday. Before you start tracing, it would be good if you would contact us and we can check that the filtering that you're doing, that the tracing requirements that you have are something that's going to be relatively reasonable. We don't want you generating hundreds and hundreds of gigabytes of data. If we can help this, maybe it's necessary, but maybe we can try and avoid it. So certainly do the profiling first, do the scoring of the profiles. You're welcome to try out using the hardware counters that are available on the Archer system, if those are of interest to you. And for the trace analysis, as I said, we would like to help you and guide you with that. So before you you start doing the tracing of your own application, let's check it together and make sure that the trace buffer requirements, I mean, you have to make sure you set the trace memory, the Scorpy total memory to the appropriate size for the trace buffers, as well as having a filter or some other configuration where the amount of data isn't going to be excessive. And then we'll hopefully get some traces that we can analyze and look at those metrics again this afternoon. Quick question I see in the chat, is it possible to select a subset of the topology to display? The topology is certainly something that you can zoom in and configure in different ways. And if you're only interested in a single socket, then I think the best thing is to look at that in the tree view. If you're So I think that's everything I hope you need from me right now. As I said, we'll take a break for an hour or so for lunch, and then we'll come back and hopefully work with you more on your own application codes or help you work through the example application with BTMZ or one of the other benchmarks if you don't have your own code.